Okay, so moving on, we know that we can reflect a graph across the line y equals x to get the graph of its inverse. All right, so we call these pairs that correspond from one to the other, we call these corresponding points, okay? So for instance, if we come over here like we did, 1, 2, 3, we call this point, ooh, I'm still in dotted line writing mode. If we call this point over here -5, comma -3, it would reflect perpendicularly, that's a great adverb, across the line y equals x to the point -3, -5, okay? We call those 2 points, they're not the same point, are they? Y'all can answer that. Are they the same point? No, they're called corresponding points. Corresponding points. They correspond to each other. Now, they may be the same point, right? But that would just be kind of coincidental. For instance, if you look at this point over here, the point 1, 1 lives on the line y equals x, right? So when you flip that around, you get the same point 1, 1. So any point that's on the mirror stays the same, but otherwise we call those corresponding points. Now, I did say why x, right? Why is x the magical line? Well, there's a couple of reasons. First of all, y equals x is its own inverse, right? There are other functions that are their own inverse, but if you want to find the inverse of y equals x, interchange x and y and resolve for y. Boom, done, easy. So that's one of the reasons. But the reason that it comes the mirror is because not only is it its own inverse, but it's the identity function. That's what we call it. It's the identity function. Your input equals your output. Your input equals your output. And that's why it becomes the magical mirror. All right. There are other functions that are their own inverse, like 1 over x, y equals -x, but they're not the identity function. Okay. So corresponding points. Let's look at this curve a little more before we venture on. We know over here algebraically that these two inverses had reciprocal slopes, but they're lines, right? They have a constant slope. The slope at any point on 5x minus 8 is the slope everywhere. What about curves, though? Curves can't have reciprocal slopes because their slopes vary, right? That's why they're curvy. But we can talk about their curve at a single, or how fast those graphs are changing at any moment in time. We can look at lines, but they're called tangent lines. Hank, we need to talk after this lesson, but I'm recording now, so not yet. What if I looked at the tangent line? Let's snap this here. Snap the tangent line at -5, -3. Snap it right there. And then let's snap the tangent line to -3, -5. I got to move it over a little bit. There it is. There it is. If I look at the tangent lines at these corresponding points, notice where they intersect, right? They intersect on the line y equals x. What do you think we could say about the slopes of these two tangent lines? They're not the same, obviously, right? But the blue line looks like it could be a slope of what? What would be a possible slope for this one? We could actually calculate it if we wanted. Not really, approximately. 1/2, good. It's less steep than 1. What would be an approximate slope for the red one? Possibly 2 or 3, right? It's steeper than 1. Well, what if I told you that if I just looked at the equations of the blue and the red, I just looked at those equations, didn't we just prove kind of in the thought experiment that the equations of those lines would end up in the same fashion that these equations of lines ended up with reciprocal slopes? Yeah, actually, yes. So if we have a curve, we can say then that, hey, the slopes are going to be reciprocals of each other as long as we're talking about corresponding points. Or to say it another word, the slope at corresponding points of inverse functions are related how? They're what's of each other? Reciprocals of each other. Yeah, inverse functions have reciprocal slopes at corresponding points. That's another way to say it. Inverse functions at corresponding points have reciprocal slopes. Okay. Now, let's talk about this, an inverse function. How are we going to identify that a function is an inverse function? Well, you're going to either be told that f and f inverse are given to each other. You're going to actually see, f and f inverse, okay? Or you might be given something like this. You might be said, let G be the inverse of f. That is, let f inverse of x, which I already told you is a cumbersome notation, let it equal G of x. G of x is not cumbersome. In other words, give them a nickname. Give them a nickname. So now f of x and g of x are inverses of each other. You might just be flat out given these two notations. You might be told that one of them is the inverse of the other, or you might be given any one of these ideas. Okay? This is composition. Notice what this says. Two functions, f and g, are inverses of each other if and only if f of g of x equals g of f of x, and they both equal x. Okay? Composition of functions in general is not commutative. Okay? If you take a $10 off and then a 10% discount, it's a different dollar amount than if you took the 10% first and then the $10 discount. Right? So that's composition. It's not always commutative, but it is commutative in one case. The order doesn't matter in which you compose them if those two functions are what's of each other? Inverses. So here's a quick illustration. Look on the floor tile. Where they meet, there's a T, right? Or if you look at it sideways at a 45, or if you're Hank, turn the floor 45 degrees. Yeah. It looks like an X, right? So let's say I'm standing right there at X marks the spot. I'm standing at X, everybody, okay? Let's go ahead and have two functions. The first function is 2 steps to your right. Ready? Here we go. 1, 2. And now how do I undo that? 2 steps to the left, right? 1, 2. I'm back where I started at what? X. Now, watch this. Watch this. I'm going to do it the other way this time. I'm going to go 2 steps to y'all's left. 1, 2. And then I'm going to undo that by going what? I don't know. 2 steps to y'all's right. Where am I back again? I'm back at X. And I just figured out what my freestyle is going to be during the dance. I'm just going to do like inverse, inverse. I don't know. I'll figure it out. I got to dance at home in front of the mirror. Yeah. Actually, I don't need the mirror. I'll just practice at home. I'll figure it out. Okay. So notice what this says. Start with X, apply G, then apply F. They undo each other. You're back where you started with X. Order doesn't matter. Start with X, apply F first, then G. They undo each other. You're back where you started with X. So you might just be told that two functions F and G have this characteristic. And you're going to have to be like, oh, composition is commutative. They undo each other. When is that going to happen? When those two functions are what? Inverses. So you might not be explicitly told, hey, these two functions are inverses. Two functions F and G have this quality. And you might be given only half of it. So you might just be told, hey, we have two functions F and G such that F of G of X equals X. Is that enough? Yeah, you start with X, you end with X. That's only when you have inverses. Or you might be told G of F of X equals X. That only happens when they're inverses. Or you might be told F of G of X equals G of F of X. That only happens when they're what? Inverses. Or you might be given all three. You have to be able to identify that two functions are inverses, okay? And now here's the next thing that jumps into your mind. As soon as you know two curves, two functions are inverses of each other, you're going to tell yourself, ooh, 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 ooh. At corresponding points, their slopes are what's of each other? Straight up reciprocals. Straight up reciprocals, not opposite reciprocals. When do we have opposite reciprocals? Perpendicular. We got to keep them straight. Perpendicular is opposite reciprocals. The sign has to change, but these are just reciprocals, okay? Inverse functions at corresponding points have reciprocal slopes. All right. Let's go ahead and go through these 3 bullet points because they're super important. Number 1, inverse functions at corresponding points have what type of slopes? Reciprocal slopes. Let's go to the next one. Inverse functions have reciprocal slopes at what type of points? Corresponding points. Very good. And then the third one, at corresponding points, what type of functions have reciprocal slopes? Inverse functions.
No.
Yeah, like the music you sent me.
He said redo it 4 times.
You sent me like 2 versions of the same thing, one after another. We got to talk about it. It's okay. We got to talk about it.
But right, you
Hey,
failed.
in your defense, you weren't here, so it's you tried. All right. Here, yeah, he did. Yeah, he just copy pasted it. Yeah, because I don't know how to replay a song. But no, he put it's like 6 minutes long. You want to dance for 6 minutes?
I thought that's what we were doing.
Okay. We're gonna dance for like a minute 45.
Extend the intro.
I was told cut it at 1:42 and repeat it 4 times. That's what Landon texted me.
Hey, we'll get it figured out.
Right.
Yeah. We just want the intro before the guy starts, before the dancing would normally start. We want that intro to be extended, just so we have time to come out of the audience.
Oh.
So he was thinking just extend the part that goes, do your dance, 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 do your dance. And then once we're all in like configuration, and then we all go boom, then okay. And then, so cut it at 1:47 so we know when to stop, and then take just the first part of the song, clip it, and then repeat it. Okay. Yeah. All right. Good. See, it helps to be here. You can't express certain things in an email, right? Or a text. Let's express what we just said in those 3 bullet points mathematically, okay? Let f and g be inverses such that f of g equals g of f, and they both equal x. Now, you're going to be given some information about a point. Let f of a equals b and g of b equals a. Okay. What does that mean? That means that on function f, there is an ordered pair called a comma b, right? And therefore, on its inverse function, which we're calling g, there is a what type of point? B comma a. What do we call that? It's the what point? Corresponding point. Corresponding point. You don't need to know both, do you? If you know one, you have the other. If you know the other, you have the one, as long as you know they're inverses of each other. So that's what this means. If f of a equals b, that's the other way to write it as an ordered pair in function form. That means there's a point on f called ab, and therefore switch them around, ba, you get the corresponding point, and that's what this means. G of b equals a. You don't have to be given both of them. Now, here's what we know. Inverse functions at corresponding points have reciprocal slopes. What's another name for slope at a point? Derivative, right? So look at this. The slope of g at its input b is the reciprocal 1 over the slope of f at its input a, right? That makes sense. Inverse functions at corresponding points have reciprocal slopes. We can rephrase that using calculus language. Inverse function at corresponding inputs have reciprocal whatatives? Derivatives. Yeah, it's the same thing. Inverse functions at corresponding inputs have reciprocal derivatives. Let's do it again. If you want to write it down, you can. Inverse functions at corresponding inputs, x values, have reciprocal derivatives. Yeah, okay, good. So why in the heck would we need to know this? Well, sometimes we may be finding or asked to find the derivative of a function's inverse, and we can't find what the inverse equation is. So what we have to do is we have to have a secret way to get in. We have to have a secret way to still find that value. And what we do is we come in through the back door. We have like a secret entrance to answer that problem. Willie Nelson plays Green Hall periodically. I had the privilege of seeing that concert several years ago. And I don't know if I told you our third period, but it was like standing room only. And there was a guy in front of me and a girl behind me, and it was pushing to the front the whole time. And throughout the course of the night, the guy's jeans in front of me was touching the front of my jeans, and the top of the girl's shirt behind me was touching the middle of my back, you know? And I was like, this is uncomfortable. But Willie, yeah, we were like touching, his butt was touching my front, and then her top was touching my shoulder blades. We were pushed in, and I was like, oh, this is awkward. But Willie Nelson made eye contact with me, and I was like, oh, it's so worth it. It's so worth it, right? I don't like that. It's gross. But Willie Nelson made eye contact with me. When Willie Nelson plays Green Hall, he does not come in through the front door. No, no. Willie Nelson, watch this. Willie Nelson, Green Hall, Willie door. Come on, show up. Yeah. When Willie Nelson plays Green Hall, they basically take one of the windows out, put steps for him, and he walks into the back of the stage. They only do it for Willie Nelson. And there he is going in through the Willie. They call it the Willie door. Okay, but really it's just a deconstructed window with steps. Who gets to use the Willie door? Willie. Only Willie.
Only Willie goes to the back.
Only Willie goes into the back door. Right? And yeah, that's what we're going to do. We're going to go in through the back door, and we're going to, it is really cool. Okay. Let me show you what I mean. Let's come down here to example 2. Right? Let's say we have f of x equals x cubed. It's a 1-to-1 function, isn't it? Let's quickly graph x cubed. We know what that looks like. Here's what the graph of y equals x cubed looks like. Or f of, I call it f of x equals x cubed. Give it a specific name. It is 1-to-1, right? It's 1-to-1. So I'm going to kind of redo the instructions. What if I want to know this? What if I want to know f inverse prime of 8? Let's start with this instead of end with it. Now, notice how I read that. That's cumbersome right there. F inverse prime. When we do the derivative of f inverse, we have to put the whole thing in parentheses. That's why it's such a good idea just to call f inverse like g or something else. Give it a nickname. Because what if I didn't have the parentheses around it and I did f inverse prime? It looks like f to the negative 11th, right? So f inverse prime of 8. Now, there's 2 ways to find f inverse prime of 8. We can either A, find the inverse function of f of x by interchanging x and y, resolve for y, and get the inverse function. And then take the derivative of that inverse function, plug in an 8, and we're golden, right? That's going through the front door of Green Hall. We're the Willie Nelsons of math. We come in through the Willie door. We're going to do it a different way, okay? We're going to do it a different way. So here's what we know. If you ever have a problem like this, here's what you start with. You tell yourself, okay, on f inverse, 8 is an input, right? On f inverse, 8 is an input. That means on its inverse function f, 8 is a what? Output. You're going to be given the original function, x cubed. You have to figure out then, what do you plug into the original function to get out an 8? And in this case, we can figure it out. It's a 2, right? Now, sometimes you're given a hint, but it's a 2. It's all about finding this. It's all about finding the f input. Okay, that's what it comes down to. Once you have that in your hand, as Harry says, you're golden, right? Because here's what we know. We know then that inverse function, the inverse derivative of at 8 is reciprocal 1 over the derivative of f at what? 2, right? They each have their own respective input. The input on f inverse is 8, but coming in through the back door, we're going to find the derivative of f at 2 and flip it. Inverse functions at corresponding inputs have reciprocal slopes. All right, now we have a plan of action. Let's go ahead and find f prime of x. What's f prime of x? It's 3x squared. And now I'm going to plug in what? Do I plug in an 8 into f prime? No, because its input is what? 2. I plug in a 2. So now I get 3 times 2 squared, which of course is 12. Therefore, if the slope at the point 2, 8 is 12, then what would be the slope at the corresponding point 8, 2? 1/12. Okay. That's how we do it. That's how we do it. If you're asked to find the derivative of an inverse at 8, you need to find what the input is for the given function. Then all you got to do is take its derivative, plug in the new input that you found, and flip it. Okay? And flip it. Now, of course, that's not the only way to do it. Here's the other way to do it. That's what the rest of this problem is. And I'll just kind of cut to the chase. If we know that y equals x cubed, we can actually change the letters around, right? Here's the money step. X equals y cubed. Let's solve for y by taking the cube root of both sides. That's the inverse function, right? So f inverse of x is going to equal x to the 1/3. Now, since we were able to find the inverse, which is a luxury, we're not going to be able to do that every time. F inverse prime of x is going to be, by the power rule, 1/3 x to the -2/3, which when we clean that up is 1/3 times the cube root of x squared. Now, since I have f inverse prime, I can plug in the 8 that I wanted in the very beginning, and I get this. The cube root of 8 is 2, 2 squared is 4, and we get 1/12. We get the same answer. But look how much more work that was. When you come in the front door of Green Hall, you got to like greet everybody. Hey, how's it going? How's it going? How's it going? Shiner Bach. Oh, you like Shiner Bach? Shiner Bach. Okay, that's good. All right. Hey, I'm trying to get to the stage. Excuse me. That's a lot of work. If you're Willie Nelson, you're just like, take me through the window. I'm on stage. Here we go. Right. Now that'll all gel as you leave here, and it'll simmer in the back end of your brain. Right. Inverse functions at corresponding inputs have reciprocal derivatives. The most important thing is that you plug in to the given function's derivative the input that you find, not the input that you're given, okay? All right. So again, thanks for everybody for all you've done so far this year, this week, and in the future. It's a real pleasure being y'all's teacher.